Hello students, in the last video lecture we will talk about the definition of the Poisson bracket, and the base of the definition we give the definition for integral of equation of motion and Poisson identity. Okay, so now the next theorem is Jacobi Poisson theorem, or you can say that Poisson theorem. So what is the statement? If f and g are the integral of equation of motion, then Poisson bracket of fg is also an integral of equation of motion. So that will be the statement. So that means what is given here, f and g are integral of equation of motion. So according to the definition, f of t qi pi is equal to some constant. That means function of some Hamilton variables return some constant value c1. G is also integral of equation of motion, therefore g of Hamilton variables is also equal to some constant. Okay. Now if you take the partial derivative with respect to t, if you take the derivative of this f and g with respect to t, so you can take that, it will be curl ft by curl t into dt by dt, that becomes 1 plus summation, because here I is varying from 1 to n. Okay. So here if you take the partial derivative of f with respect to qi into curl qi by curl t, okay, dqi over dt, you can say that that will be dqi over dt, then curl f over curl pi into dpi over dt. Okay, since I is varying from 1 to n, so I take that summation is I from varying from 1 to n. So it will be the partial derivative of f with respect to t, that will be there. Now you know that this is dqi over dt, that means qi dot, and this is pi dot, but we know that the Hamilton equations was qi dot will be equal to curl h over curl pi, okay, where h is the Hamilton function of Hamilton variable t qi pi, okay, and pi dot is equal to minus of curl h over curl qi. These were the Hamilton equations as we have discussed in the previous lectures. So this is qi dot and this is pi dot. You place its value, so its value is curl h over curl pi and its value is minus curl h over curl qi. So I take the minus outside and this is curl h over curl qi, right? So this summation, if you combine this summation, so it will be of this type, summation curl f over curl t plus summation of this thing, that will be equal to 0. Now you know that what is this one? According to the definition of the Poisson bracket, this is the Poisson bracket of f and h. Okay, so curl f by curl f t as it is plus Poisson bracket of f h is equal to 0, right? So you will get this equation by using the first. Now similarly, if you use the second equation, you take the partial derivative with respect to t and using the definition of the Poisson bracket, so you will get that curl g by curl t plus Poisson bracket of gh is equal to 0. Okay. Now you have to prove that, what you have to prove? You have to prove this Poisson bracket of product of these two functions, that will also be the integral of equation of motion. So it will be given by, that means you have to prove curl by curl t of this Poisson bracket of fg plus Poisson bracket of fg and h, that will be equal to 0, right? So this one I want. If I consider the LHS, you will say that curl by curl ft of Poisson bracket fg plus Poisson bracket of fgh, that will be given by. Now use the property for the Poisson bracket. How to take the partial derivative of Poisson bracket of fg? That will be Poisson bracket of curl f by curl ft into g plus Poisson bracket of f into curl g by curl t, and the remaining term will be as it is, right? Now we use the value of curl f by curl t as in the above given here, curl f by curl ft plus Poisson bracket f h equal to 0 and curl g by curl t plus Poisson bracket g h equal to 0. That means its value will be equal to minus of f h, and this value will be equal to minus of Poisson bracket g h. So I place this value over here. Its value will be placed here and its value will be placed here, right? And this term is at stage here. Now you know if I am using minus of fh g plus minus of f into Poisson bracket gh, then whole Poisson bracket plus of this term. Now again we use the property for the Poisson bracket. What is that? You know, if there are the two functions, suppose phi and psi, Poisson bracket of this thing, if we change the order, that will be minus of Poisson bracket of psi into phi. Alright, so I will say that this fh can be written as hf, so that will be minus minus becomes positive, so hfg, right? If I change the order, this is first term f and second term is gh, so I change the order, so that minus becomes plus and plus of this term. Okay, now you know that there are the three functions h, f and g, all are the functions of Hamiltonian variables. Okay, so by using hfg plus Poisson bracket of ghf plus Poisson bracket of fgh, by using the Poisson identity, that summation will be equal to 0. Okay, so if curl by equality of Poisson bracket fg plus Poisson bracket of fgh, this is equal to 0, so that means this is the integral of equation of motion. So that is the Jacobi Poisson theorem, right? So this is the proof of the Jacobi Poisson theorem. Now the next definition is integral invariant action, okay, in Hamilton sense. So let's we consider an holonomic system with Lagrangian function L as a function of t, qi and qi naught, okay, where I is varying from 1 to n, right? Now if we take the integral of this L with respect to t, where limit is varying from t0 to t1, then this is known as the action, which will be denoted by w. So this is the action in the Hamilton sense, okay, within the time interval t0 to t1. And this term L dt, this is actually known as the elementary action. Okay, so now is the state path. So what do you mean by the state path? So the same, if the function L is a function of t, qi and qi naught, so for the action, to complete the action, we define this qi as a function of t, okay, within the time interval t0 to t1. That means action within the interval t0 to t1. So what will be the state path? The system will be move along the state path. Let me tell you again by using this one, right? So if I take that n plus 1 dimensional space, okay, where m naught is a function of qi and t naught, okay. Similarly, this m1 is qi and t1, right? So I is varying from 1 to n. So this is a n plus 1 dimensional space. So if I denote, the system will be move along, initial point हमारा यहाँ पर क्या है? This is m naught and the final point is here m1. So I will say that the system will be move along the state path. System will be move along the state path if this qi satisfying the Lagrangian equation. Okay. So for the state path, you say that for the state path, the function qi of t, that will satisfy the Lagrangian equation. And what is the Lagrangian equation? d by dt of curl L over curl qi naught minus curl L over curl qi equal to 0. Here I is varying from 1 to n. Okay. So accept this state path. Accept this state path where qi satisfy the Lagrangian equation. All the other paths are known as the circular paths. Okay. So this all other paths is known as circular path, which is varying for passing through m0 to m1. Okay. So now the next is our Hamilton principle. So what is the statement of the Hamilton principle? That is the action W. The action W has an extremal, or you can say the stationary value for the state path as compared with the circular path. Okay. केवल स्टेट पाथ के लिए एक्सट्रीमल वैल्यू देगा when it will be compared with the circular path. And what does it mean? That means delta of W will be equal to 0 for the state path. Okay. So this thing I have to prove actually. Now I consider that x and w is given here. So I consider an holonomic system with generalized coordinate qi and Lagrangian function is a function of t qi and qi naught, where I is varying from 1 to n. Okay. And we know that the definition for the action will be denoted by w, that will be given by within the time interval integral of L t naught to t1 dt, right. Now we are considering the paths. So what you are doing here, we are considering the family of the paths actually. So we are considering any arbitrary family of the paths of one parameter alpha. That means qi was the function of t, but here we are denoting qi as a function of t and alpha. Okay. So the family of path of one parameter alpha we are denoting. Here this t is varying from t naught to t1, and this alpha is varying from minus gamma to gamma, where gamma is some integer. Okay. So here alpha corresponds to the straight path or straight line, and alpha non-zero correspond to the circular paths, right. So we know that all the paths having the common point, as we have shown the above figure, all the above paths like this, figure will be like this. Okay. All the paths have the initial point m0 and the final point will be m1. Initial point means that will be qi and at t0. Okay, and that will be m1, qi and t1, right. So similarly this thing I have shown qi as a function of t and alpha. So you say that all the paths having a origin, that means the initial point m0 and the terminal point as m1, where qi naught means qi value at t0 and alpha, and qi1 that will be means by qi at t1 alpha, right. Now you have to find out the, actually you have to show that delta of w will be equal to 0. So I make w. So now w is given by integral t0 to t1 of L dt, but what is L? L is a function of t, qi and qi naught. Okay, but qi is again a function of t alpha, right. So I write down the same thing. So when you take the integral of this thing with respect to t within the limit t0 to t1, so that becomes a function of alpha actually. So I denote this is w as a function of alpha. So you say that delta of w, if I take, so it will be given by delta of this integral, and that will be given by integral of delta L. Okay, that means the variation of the function L. So L is a function of t qi and qi naught. So you take this delta, that will be the partial derivative of L with respect to t into delta t plus summation I varying from 1 to n, partial derivative of L with respect to qi into dqi or delta qi plus partial derivative of this L with respect to qi naught into delta qi naught, right. But when we are considering the variation of the function, you know that the independent variable will be considered as constant. So t will be considered as constant. If t is constant, so delta of t will be equal to 0. So that means this part will not be there. Okay. So remaining that part will be integral of summation this one, right. So if we take the separate the integral of this term plus integral of this term, I take this one. So keep this as it is, and we open the integral. Integral of the summation can be written as summation of the integral. Okay. So when you take the summation of the integral, so there are the two terms. So you take the integral by using the by parts. So I am using that, and we are solving this by using the by parts. This term as it is, first function as it is, integration of second. You can check this. This is first function, this is second. So this first as it is, integration of second, and we obviously summation is outside, I varying from 1 to n within the limit t0 to t1, and minus integral of derivative of first into integral of second. Okay, that was the actually summation of the integral, but you can change it as integral of summation. Okay, that will be the same. So when you collect the terms, take its first as it is here, dash term to the second term, and this will be the value of this at t1 minus value of this at t0. Okay, but we are showing that that all the paths having the initial point m0 and the final point is m1. That means the value at t0 and t1, the points are fixed. If points are fixed, so that means qi is fixed. If qi is fixed, that means delta of qi will be equal to 0 for the initial and the final point. So if qi as initial point, this one, so therefore delta qi at initial point 0 and delta qi at final point, that will also be 0. So that means this part will be removed. So we are left with only this part. So we combine the part. When you combine this one, so you get integral t0 to t1 summation I vary from 1 to n curl L over curl qi minus dy by dt of curl L over curl qi naught delta qi is dt is equal to 0. Okay. Now, but we are interested to find out the delta of w for the state path. Okay. But for the state path, you know that for the state path qi satisfies the Lagrangian equation. And what was the Lagrangian equation? That was d by dt of curl L over curl qi naught minus curl L over curl qi, that will be equal to 0. Okay. So here if I take the minus common, so that will be the integral equation, I mean the Lagrangian equation, and Lagrangian equation having the value 0, so that means this value will be equal to 0. If this value is 0, so you will get that delta of w will be equal to 0. So that means for the state path you will get delta of w will be equal to 0. Right. So this proves the Hamilton principle, Hamilton first principle. Right. Now if you take the conversion of the Hamilton principle, so what will be the conversion? So conversion means when state path is given, so you have in the state path is given, then you have to prove that delta of w equal to 0. But in the converse part, if delta w equal to 0, so you have to prove that path will be state. Okay. So I take the converse of the Hamilton principle. For some path, if delta of w equal to 0, so you have to show that that path is nothing but the state path. Okay. You have to prove this one. So I take that delta of w is equal to 0. If delta of w equal to 0, what was the w? W was integral t0 to t1 L dt. Okay. Where qi as a function of t alpha. Right. So when delta of t is there, the same as we done before, the same thing you have to take curl L over curl t delta t plus summation I varying from 1 to n curl L over curl qi delta qi curl L over curl qi naught delta qi naught, that is equal to 0. Right. For the variation of the function, t is fixed, therefore delta of t is 0. So that means this part is removed. If this part is removed, so we are left with this one. Okay. If we are left with this one, so again separate the integral of the first term plus integral of second. So you can take the summation outside also. So I take that integral of the summation. Right. Actually this will be, firstly you have to take the summation outside, then integral, then again you have to take that integral of summation. So I skip the step and I write down over here like this. Okay. So that will be as it is here. You apply the integral by parts over there. So you apply the integral by parts and you get this one. Okay. So what you got? You get that this part plus curl L over curl qi into delta qi at t0 and t1. Again you know that t0 and t1 are the initial and the final point. For initial and final point, qi is fixed, so therefore delta qi will be 0 for the initial and final points. So that will be 0. So this part will not be there. Okay. So this part will not be there, and delta of w we are considering 0. So that means you are left with this term is equal to 0. Okay. This part we have already eliminated for the initial and final point. So which is written over there, and the remaining part we got this thing. Okay. But here you check that delta of qi, this is actually the arbitrary. Okay. So arbitrary, delta of qi is arbitrary. So you say that if integral of this term is equal to 0 and this is arbitrary, so you say that obviously this remaining term will be equal to 0. Okay. And remaining term is curl L over curl qi minus dy by dt of curl L over curl qi naught equal to 0. Okay. Or you can say that you can take the minus sign common, that will be dy by dt of curl L over curl qi naught minus curl L over curl qi equal to 0. Okay. So what does it mean? That means qi is satisfying the Lagrangian equation. Okay. If qi as a function of t and alpha, that is satisfying the Lagrangian equation, what does it mean? that means the path along which the system is moving, that will be the state. Okay, so that was the proof of the Hamilton first principle. Now in the next class we will discuss about the Hamilton second principle. Thank you very much, students.